Recording's rolling. It is Tuesday, September 16th. Yesterday, at the end of class, I was most way through the dynamics overview, that PowerPoint. So I've got a few more slides. We'll try to do these as fast as possible. And then we're going to move on to the spring skills lab. You guys have this lab page. It's really like 10 mini labs. And you know what? Actually, I think it's kind of worked out because some of the slides I'm going to go over today actually are some of these mini labs that you guys are doing. All right, so let's do this PowerPoint, pick up about where we left off yesterday. And then we got that a little bit on live. Right, so because I want to introduce all these ideas, like plant all these ideas in your mind. Incline puzzles are common in this class. Yes, like some blocks, some weight on an incline. Because if you change this angle, did that maybe change how it slides down?
Yes.
No, guys, look at how many forces do I have on this block?
2, 3.
Yeah, 3, right? You guys see the weight straight down? Says, oh, guys, what's this force called that's perpendicular to the surface? Normal force, because normal means perpendicular, doesn't it? Yeah. Right. And then I also have a friction force here. Now, here I'm showing this in equilibrium. Do you guys see how the 3 forces kind of cancel out? They sort of cancel out. If you connect them all tip to tail, the net force would be equal to what? Zero. Right. Hey guys, 0 net force. Does that mean necessarily 0 velocity? Not necessarily. So you guys see in blue, I said there's 2 possible conditions this could apply to. It might be a rust. It might be, right? Or it might be sliding at constant velocity. And if you just have the picture, like that free body diagram, it's ambiguous. You don't actually know which category it is. Okay? Both of those would be 0 net force, 0 acceleration. Okay. There's also, here, this one just focuses on that normal force as a function of the angle. You guys see how if it starts out flat, the normal force is equal in magnitude to the weight. But as you ramp up that angle, make it closer to vertical, you guys see that blue normal force vector getting shorter? Right, and here's the expression here, that connection. Right. And then what else can you do with inclines? What if you have a 0 friction incline? Actually, you guys did have one of these already. You guys remember your car and incline lab? You guys think this page right here is pretty well models your car and incline lab? Right, how it goes down. I may have shown this to you briefly before too. Okay? Or here's something a little different. What if it slides down at constant velocity? I'll have you guys do this probably the next couple weeks. Which is different. Guys, constant acceleration and constant velocity, are those 2 totally different things? Yeah, because the acceleration would be a changing velocity. It has to be. Right? Versus a constant velocity would be a 0 acceleration. All right. What could that tell you? Right. So again, just planting these ideas today. This is one of your setups today. I'll have you guys take a spring scale and just very simply hang some weights from it. Right. But you guys see 2 forces. I got the weight down, I got the spring force pulling back. And guys, anything that's equilibrium always means the sum of the forces equals what? 0. Yeah, so net force is 0. Doesn't tell you anything much about velocity necessarily, but acceleration would be 0, net force is 0. Oh, here's another one you guys are doing today. So maybe run a little hypothesis in your mind right now. What if you have like 1 kilogram, 1 kilogram, 1 kilogram? What do you think these spring forces are, spring scales are reading? 1 kilogram, by the way, weighs almost 10 newtons. It's like 9.8 newtons. So I think the bottom one would read like 9.8 or 10 newtons, I think. Okay? You guys can find out for sure later. Okay? Let's go into 2 dimensions. 2 dimensions. Here's another one I'll have you guys do today. What if you have a weight hanging straight down, supported by 2 spring scales at angles? Ooh, maybe you could take a protractor. There's a bunch of protractors back in the lab area. You could like measure some angles. Could you do that? Now, if it's symmetrical, guys, if it's symmetrical, do you think these spring scales would read the same number ideally? Like if you support them the same? Right? Now, how we're going to make sense of this eventually. Do you guys see how I took these spring forces, these diagonal forces, and I broke them down into components? You guys, look at this horizontal component to the right and this horizontal component to the left. What do they have to add up to? 0. Yeah, or they same magnitude, so they zero out. Right? It's opposite directions. Right? And then whatever this weight is, suppose this weight's like 10 newtons. What do you think this upward component and this upward component each are? Yeah, so you think like 5 and 5 up could 0 the 10 down, right? So 5 and 5, the minus 10 would go to 0, right? Right. Let's get a little fancier. What if the angles are different? I guess you can try this today if you want to. I don't have a mini lab for it, but if the angles are, but the guiding principle is the same. If you take these diagonal forces, guys, everybody look up here. Guys, look up here. Look up here. Pay real close attention. Right. If you take the diagonals and you break them into components, the left and the right cancel out, and this up plus this a little bit up minus this down also have to 0 out. There's a lot of cosine and sine floating around. You guys see that? A lot of cosine and sine. Right? How about the floor you're sitting on right now? Do you think the engineer who designed this building, maybe they had to check every single point in the floor? I bet there may be some, makes it look kind of like this, maybe some truss system, and make sure that the materials they build the floor with are going to hold us up. We're going to go crashing down on the first floor. All right. Oh, actually, this is one of your mini labs today. You guys have a table that looks a lot like that. Okay, I might have you guys do this one day if we have time. I like this one. Elevator physics. You guys ever step on a bathroom scale in an elevator? Well, I mean, maybe, right? You've been in an elevator though, right? The elevator starts to move, and then you can feel it start to move, and you can feel it come to a stop. And then whether you're going up or down, maybe it feels a little differently too, right? But what about here's a bigger picture, because this slide is like a derivation. This slide is showing like the three categories of situations: accelerating down, accelerating up, and in the middle is no acceleration, which might be a rest or might be constant velocity. Those are both zero acceleration, right? All right. Okay. Ooh, Atwoods. So I'll give you guys. I have a little red pulleys, so those are also back in the lab area if you want to play around with them a little today, right? So you put different lab masses, right? How does the thing accelerate? And then to connect this back to kinematic motion, if you can ultimately figure out how much it accelerates, can you go on to figure out maybe how far it's moved and how much time, kind of thing, right? Maybe the college equation could do that. Here's what's sometimes called a modified Atwood, right? Where maybe one of these has a horizontal type motion. I'll put it on little wheels right here, get rid of most of the friction. Right. And then, can you combine an Atwood and an incline? So those are especially fun. Right, so that's as far as I'm taking this presentation today. Right. So let's go over to, and some of the slides you just saw show up also in these mini labs. Right, so let's look at these. Hope you guys got a little bit. Make sure you guys know what you're looking at. So if you guys write your name here, write your names. Okay, so the first one, I just want you to take different lab weights. You guys have a whole box of lab weights here. And attach different lab weights to a spring scale. What's the mass, either in grams or kilograms? Right? And then what's the corresponding force rating in newtons? Spring scale lab. Look, I got to show you guys the spring scales. I'm being silly. So I got all these spring scales. And if I put them sort of in order, I think they go in this order in terms of stiffness. Did I get that right? I think so. So, guys, the green one only goes up to 5 newtons if you stretch this whole thing. You guys see how loose that is? Okay. Is that a very small spring constant? It's really easy to stretch this. Okay. Put a little. This one can only hold the little weights. Right? The brown ones are kind of the medium type. So this goes up to 10 newtons. Right. So kind of versatile. All right. So it feels a little stiffer. You can feel it. Okay. The red ones go up to 20 newtons. They can hold like twice the weight that the brown ones can. Yeah, that's getting pretty stiff right there. And then this white one goes up to 30 newtons. 30 newtons. Can hold 3 times the weight of the brown one. And the gold one goes up to 50 newtons. 50 newtons. You guys can try that too. Be a strong man. You're working out. You're working out here. Like all sorts of niggas. On the side it says N for newtons. Guys, N for newtons. That could measure a force, right? Like a pulling force. Okay. On the opposite side, careful, guys. On the opposite side, it says G for grams. Now, guys, if you're trying to measure a force, so you're going to measure in newtons or grams. Yeah, let's go with newtons, right? The idea of grams only works if you're at the surface of Earth, and like what mass would result in a weight that would stretch it so far, right? Like this is 200 grams. So if I try to stop this and show you guys, it does show 200 grams. But on the weight side, it really shows it's like 1.96 newtons. So you get like 2 newtons. I might just call it 2 newtons. Okay. Yeah. All right. So there you go. There's your spring scales introduction. All right. Let's go here. All right. Next one. What I want you guys to do is to take one lab weight, take 2 spring scales, and kind of shift them back and forth. Can you guys do that? Like if you hold this evenly, if this is a 5 newton weight, you think it splits like 2.5 and 2.5?
Yes.
Right. But what if I put more on one side? What if this side's holding 4? What do you think this one's holding? Maybe 1, because 4 and 1 maybe add up to 5. Or I don't know, maybe you can find out for yourself. Maybe you can record a bunch, what's the force rating on the left and the right at the same time, and get sort of like coordinates, like XY coordinates. Can you guys plot that? I wonder what that graph is going to look like. The force on the left side versus the force on the right side. Let's figure that out. Let's go 2-dimensional. So what if you make this Y shape? Now, for this one, start out straight vertical. Suppose you got like here, I'll call this a 10 newton weight, which I don't have them within reach, but I do have one within reach. Forgot about this guy. Here. Suppose you hang on a 10 newton weight. Do you guys think the bottom spring scale reads 10 newtons? And what do you think each of the top ones probably reads?
5.
5 and 5? Yeah, probably makes sense. Although you'll find out for sure by doing some science. Then what if you start to spread these out like a Y? And be careful to distribute them evenly so the left and the right match each other. Right? And then make it closer and closer to a T shape. Now you'll also have back there a protractor. Now notice the angle I want you to measure with respect to with respect to the vertical. So if these arms come together, you can sort of extrapolate and find like the center of the Y. Can you guys find the center of the Y dot right there? And put the node of the protractor right there. And you can hold it vertical, so it zeroes out vertical. You can sweep out this angle. You guys see that? Guys, if this was a perfect T, suppose it was a perfect T, what would this angle of theta be approaching?
180.
90 degrees. 90 degrees. With respect to the vertical, right? You guys down on paper? 90? Okay. That's why on this graph, it only goes up to 90 degrees. What do you think the force rating in each top spring scale is going to look like? And then a couple of follow-up questions. Ooh, the chain gang. Here, do you guys see the chain gang on the PowerPoint slide? By the way, there's also an alternate version of the chain gang where you turn this to the side. What if you have a train, a choo-choo train? Choo-choo. You got the front engine pulling all the boxcars behind it. Caboose is right in the back. Okay. And it's supposed it's accelerating. That might be sort of similar to just hanging these weights. Huh. All right, what if you slip another one in there? Okay. On the back side, what if you start putting these in motion? Hey, that elevator. Do you guys just see some elevator slides? What if you accelerate this up versus accelerate down? Now, there's more I want to say on that, but maybe I'll see how much you guys can figure out about this. Okay. Here, I'll say this, guys. Is acceleration and velocity, are those the same thing, or are those totally different concepts? Those are totally different concepts with different units. And if it's moving up, then it definitely has an upward velocity, but it may or may not have an upward acceleration. Maybe it does, maybe it doesn't. It depends how you're moving up. The same thing with down. This one on the right, there's some string back there. There's also these little red pulleys, so you can hang some string over it. What if you accelerate this right and left? Actually, this one are very, very similar. This one I give you some like guided multiple choice questions though. Okay. If you want to, you can slip one of these pulleys right here, or I'll leave it up to you. Okay. If you keep a pretty good pace, you might get up to about this point. This one friction, like what if you drag a weight across the table surface versus if you lift it? Can you report that? If you run out of time about there, then that's pretty good. So you pace yourself pretty well. Turn this in at the end of class. Again, if you don't have the last couple, I don't really care so much. And my plan is tomorrow to debrief this with you guys, show what some ideal answers would look like, and then what the physics concepts that show up in like all these different puzzles you guys did. All right, so you guys got the rest of class to do as many puzzles as you can. I will walk around and help you guys out.